Hello everyone, welcome to Andy's Sky Dream. Today, let's go quantum. I first learned about atom in my 8th grade science class. However, this picture only shows us a 2D structure of an atom, which is a classical picture that we have all seen in our textbook. But have you ever wondered what an atom would really look like in a 3-dimensional world, in our real world? Well, that is a question that I've had since 8th grade. On ptable.com, fortunately, they provide us with an accurate 3-dimensional atomic structure of any element. So as you can see right here, if we choose a random element from ptable.com, and down here, this will show us the real-life atomic structure of this element. As you can see, the biggest difference between this one and the classical model that we have all seen in our textbook is that this one shows sort of like spherical regions where the electrons might be. Whereas in the classical model, electrons should only be in like circles or electron shells outside the protons and neutrons. So which one is correct? Well, in real life, the one on ptable.com, which is this one, is the actual case that's in our 3-dimensional world. This one, the 2-dimensional model, is called Bohr's model, and this only exists in the theoretical realm. In real life, things do not work like this. Now, another question that you might have is that since we have electron clouds, then how do I know where exactly the electron is? Well, that is a very good question. But before we get further into this question, we have to talk about something else, which is called wave-particle duality. This phrase simply means that any matter in this world can behave both as a particle and as a wave. Well, notice that it is not behave either as a particle or a wave. It is both a particle and a wave at the same time. If this is the first time you're hearing this concept, it may be very confusing. What does it mean by particle and a wave at the same time? Well, we actually interact with this concept in our everyday life. Now I want you to imagine a beam of light that's shooting right here. So we all know that light are electromagnetic spectrum, which means that the light that we can see, every color that we can see exists in the visible spectrum, which is something that looks like this. I am sure this is something that we have all seen. However, if you think one step further and sort of just review of some of the concepts that we've learned in our chemistry class, you will also know something, a particle called photon. Well, what is photon? Photon is what makes up light. Well, now here's the question, is that since light is made from photon, then how can it be a wave, right? Well, then aren't you saying that each individual photon are wave? Well, are you saying that is a true argument? Well, in fact, it is true. And this is what we've been interacting in our everyday life, and yes, we don't really realize it. Well, then how did scientists realize this point in the first place? They did something called the double slit experiment. Well, this experiment can be very complicated, but to put it in simple terms, is that if you imagine two walls right here, one right here and the other one right here, and for one of the walls, you open two slits. And then if you shoot some electrons, shoot some particles from the other side of the wall, what's likely going to happen? Well, if the electrons is coming from this way, then very likely a majority of the electrons are going to bounce back, right? Because they hit the wall. However, there are a few electrons that are going to go through the slit and then hit the other wall, that's on the other hand. It is the electrons that went through those two slits that are making a pattern of waves. So as you can see in this picture, this is what the electrons will look like from the other side of the wall. And as you can see, there is a certain repeating pattern in it, and this resembles a lot like a wave. So this is called the double slit experiment, and it is how the scientists first confirmed that electrons or particles can have wave-like property. So this is the simple term of wave and particle duality. Okay, so now we know that an electron can behave both as a particle and a wave. Well, here you might have a question. You just said everything can behave as a particle and a wave. Well, why don't you see me behaving as a wave? Well, this is because according to the Bohr wavelength, and this m right here is going to be the mass, which means that if the mass is bigger, the wavelength is going to be shorter. And for me, my mass is going to be a lot larger than the mass of an electron. So my wavelength is going to be very, very small. In fact, it's going to be even smaller than the diameter of an atomic nucleus. Well, if that's the case, then of course you wouldn't see me behaving as a wave. But on the microscopic scale, are you going to see me behaving as waves? Yes, you will. Okay, now, so let's come back to the question. Where exactly is the electron? Now we know that this region, this electron clouds, is where electrons can be, but where exactly is it? Well, this is the interesting point, is that we cannot know where exactly this electron is. Physicists can only know the probability of an electron appearing in a certain region, and they cannot know the specific place. And how do we know what this probability will be? Well, the wave function is what tells us the probability of it. So what is the wave function? Okay, so now in order to understand what a wave function really is, we have to do an imaginary experiment. So imagine that there is a box and there is a particle inside the box, let's say an electron. And the two sides of the box, the two walls, are infinitely long to prevent effects like quantum tunneling. So we're saying that quantum tunneling, things like that, it doesn't happen. And the electron has to be in the box. Okay, so now let's simplify the experiment a little bit. Let's imagine that the electron can only move in one-dimensional space, which means it can only go forward or go backward, cannot go up or down, in and out, can only move in one-dimensional space. Okay, so this is pretty much our experiment, right? We have two walls, and an electron can only move in a one-dimensional direction. Okay, so what the wave function tells us is something that looks like this. Okay, so what it's essentially saying is that what is the probability that the electron will occur, say, right here? Well, then if we go all the way down to the wave function, we can see, okay, well, this is the probability. This is how probable it will be that the electron can occur at somewhere like this. Well, then this is, as you can see, it's pretty obvious that this is a sine function. Right here, this is the highest possibility, and also this is the highest probability. But then there's a problem, is that there is no negative probability, right? You can't say that there is a negative 20% chance that it will rain tomorrow. So how do we deal with this? Well, since this is a sine function, it means we can do some transformation to make it positive. And what we're going to do is, if we simply square the wave function, and then this sine curve will be positive. So after we square it, this is what it's going to look like. So as you can see, at those 2 points, here are the highest probability that the electron will occur. Also, as you can see, since the electron cannot be inside the walls, so the probability that the electrons will be outside the wall will be 0. And the probabilities of the electron be outside of the other wall will also be 0. Well, another thing you might notice is that here there's another section that's inside the box, but the probability that the electron will be in there is also 0. Well, then how do we interpret this? Well, in fact, this is fairly simple. If we take a look at a graph like this, which is the electron configuration. So at the center, I've got a nucleus for you guys. And here, this is the first shell of electrons, second shell of electrons. This 0 probability simply means this empty white space over here. So there's a 0 probability that the electron will be in some place like this. And also 0 probability that it will be like outside of the atom. And 0 probability that it will be like some place like this, like right beside the center of the atom. So this is how we can interpret this drop in probability inside the box. And for a more accurate picture, it is in fact something that looks more like this. However, I cannot draw something that is as accurate as this. So this is simply a rough sketch of the electron configuration. Okay, so now we know how to interpret this graph. Now let's actually do some calculations. So if you want to say, well, what is the probability that the electron will occur in this region, let's say like from A to B? So what is the probability that it will occur in this region? Well, then the simplest way to do it is to find out the area of this shaded part, and the area will just be the probability. Well, then how do we find the area of a curve? Yes, that is correct. Use an integral. So as we can see, the probability of A to B is going to be the integral from A to B of the squared sine function, function. This is pronounced as psi, the wave function, and dx. So after we calculate this out, and there might be like a specific equation for your psi function, and you just square it first and then take the integral of it, and then you can find the probability that it will occur between the interval A to B. So this is how we can actually utilize this relation in our real life. Okay, so now we have learned what wave function really is. However, there's also one thing to notice is that the wave function can only tell us the probability that it will occur between certain interval on the x-axis. However, what is the probability that it will occur on a single point on the x-axis? It will be 0, because there will be no area, right? It will just be a line. There will be no area to calculate. So the probability that the electron will occur on a single place on the x-axis is going to be 0. And this is also true, is that for this, you cannot really observe it. So the reason why we have this whole probability thing is that we cannot observe where the electron really is. Because when an observer observe where the electron is, we sort of intrude the environment of where the electron is. This is called a collapse of the wave function. But this is only the Copenhagen interpretation. There are also other interpretations like the many worlds interpretation, where it says that once you observe, there is a parallel universe that's separated from the ones that you're in right now. And every time you do something, sort of like the universe split, and that is the many worlds interpretation. However, I'm following the Copenhagen interpretation here. Okay, so now up until this point, we have been talking about the wave properties of an electron. Now let's actually talk about the particle properties of electron. But before we do that, there's one thing we have to make sure is that for a certain mass, for any mass, the total energy of the mass equals to the kinetic energy plus the potential energy. And we all know that the kinetic energy is going to be 1/2 mv squared. And this is true with quantum mechanics as well. And how can we go quantum without mentioning Erwin Schrodinger and his famous Schrodinger's equation? The Schrodinger's equation may look very complicated, but in fact, it's pretty simple. It is simply the kinetic energy plus the potential energy equals the total energy. And in fact, there are 3 kinds of Schrodinger's equation that you might see. And let's sort of take a look at what each of them tells us. Okay, so this is the 3 types of Schrodinger's equation that you're going to see. I know, it looks very overwhelming, but it's fine. Let's dissect them one by one. So pretty simple. This is going to be the kinetic energy. This is the potential energy. And this is the total energy. So essentially, this is saying is that kinetic energy plus potential energy equals total energy. And this is it is true with all other kinds as well. But the first one that we're seeing right here is called time-independent Schrodinger's equation. And what this essentially means is that the energy does not change over time. So the energy remains constant. And this is in the one-dimensional space. And for this one, this is also a time-independent Schrodinger's equation. So these two are pretty much the same. However, this one is in 3-dimensional space. And from here, you can tell that here you have this symbol. This is called del. And what this actually means is the partial derivative. So what this means is you take the partial derivative with respect to s, partial derivative with respect to y, and lastly, partial derivative with respect to z. So the 3, as you can see here, the three coordinates in 3D space. So these two are both time-independent Schrodinger's equation. The only difference is that the first one is in one-dimensional space, and the second one is in 3-dimensional space. And the last one is called time-dependent Schrodinger's equation. And what this tells us is that energy does changes over time. So as you can see, this term, this is the same in every equation. And this is called h bar. H bar means a Planck's constant, a constant. And then this is m, this is the mass. And this is the symbol of partial derivative. And as you can see, we have the symbol, we have the variable t right here, which means that psi, the wave function, will change over time. So partial derivative of psi and times the potential energy and psi. And lastly, we have this over here. I just means the imaginary number, this, and h bar, Planck's constant again, and then partial derivative of psi. Okay, so these are the 3 forms of Schrodinger's equation. Well, the easiest one is going to be the first one because it is time independent. We don't have to consider time, and it's in one dimension. And what this equation really tells us is that what psi will be. So Schrodinger's equation will tells us what the wave function will be. Eventually, what we're trying to get is psi over here. It's this psi. Okay, well then what's one possible solution of Schrodinger's equation? Well, let's take a deeper look. Okay, so this is one possible solution of the psi function. Well, yeah, looks very overwhelming again, but it's fine, it's fine. Let's take a deeper look at it. So as you can see, we have 2 variables right here, x and t, and this is what is gonna look like. But there is a way to simplify this. And here I've got the Euler's identity for you guys. And well, it's pretty obvious to see that the psi function, the psi solution of this is just a different form of the Euler's identity. If you wish to learn more about Euler's identity, check out my previous video. So if we simply regroup all these terms, you see we have both amplitude in here. So if we just take amplitude outside and then keep cosine. Okay, so if we just regroup it like this, and this is gonna be the imaginary number, and k times x minus omega t. All right, so this would just be right. If we see this whole term as theta, then we can write it in the form of this. So the psi function would just be. Okay, so if we simplify it, this is how it's going to turn out. And since we're only considering one-dimensional, time-independent Schrodinger's equation, so we don't really need a t right here. So this would just become, okay, so this is what we're going to need. This is the solution of Schrodinger's equation, time-independent in one-dimensional space. Okay, now we have psi settled. Let's take a look at the time-independent, one-dimensional Schrodinger's equation. Okay, so if we assume that there's no potential energy, which means that this is going to be a free particle. Potential energy means that sort of like the field that it will have only a particle. Well, then if we assume that this is a free particle, it's inside a box, only move one-dimensional, there will be no potential energy, which means that this term will be zero. So this whole term, this term would just be cancelled out. Okay, so let's rewrite the Schrodinger's equation. Okay, so this is how it will become. And just like we have mentioned, this term is the kinetic energy. This is the potential energy, and this is the total energy. So now, without potential energy, what we are left out is kinetic energy is directly equals to total energy. So there's only kinetic energy in it. Well, now we can actually do some calculation and see if this whole thing matches. So if we just plug in what psi is from our previous equation and take the second derivative of it, and then we can begin to see. Okay, so it will be. Okay, so now let's focus on this term. Well, let's take the first derivative of it. As we can see, this is from some product rule, right? Just copy A down, and then this will be IK, right? You just copy E. And then this will be up there, since this whole thing is going to be a constant. So this is going to be the first derivative. And if we take the second derivative, and then this is going to be IK, another IK, and then E to the IKX, right? So this will be A times I square, K square, E, IKX, right? So this is the term. So now if we put this term back onto the term that we already have, it's going to be, right? Okay, so this is what we're going to have. And as you can see here, I is going to be the imaginary number, and so I square would be -1, right? So if we put I square up here, then this negative sign is going to get canceled. Okay, so let's rewrite this. Okay, so this will just be here. And if we put this k square up here, it's going to be like this, right? Over 2m. And let's leave A inside. So it'll be like this. Okay, so this is what we're going to have, right? But then you notice that this term comes back up to the side that we have just solved. So this is what's psi, right? So we can simplify it again to this. Now this is what we're going to have. And another thing we're going to know is, according to the Broglie relation, momentum P equals h bar times k. And this k is going to be the wave vector here. And this is actually the momentum vector, and k is the wave vector here. So if we plot this relationship in there, you can see that here, this is h bar k, right? This is h bar square and k square. So this means P squared equals 2m over 2m. Right? So this equation, this relation would stand. Right? And now we can pretty much see that if we come all the way back to the original equation, we will know that Ke, kinetic energy, is equals to 1/2 mv squared. And we also know that momentum equals to mv, right? This is momentum. So we can sort of correlate these two equations, right? So if we square the momentum, it would be m squared v squared, right? And then we put a m under it, and then times 1/2. This basically means the kinetic energy, because this m squared and m we just cancel out, which leaves us m times v squared. So m times v squared times 1/2 would just be the same. So these two are exactly the same. Okay, so we can rewrite the kinetic energy in this form, right? But we also know that this is p squared, right? So kinetic energy equals the p squared over 2m. Now our way of proving the Schrodinger's equation is done, because what we have up here is this, right? But then this is exactly the same with the kinetic energy. So it would be kinetic energy times psi equals to total energy times psi, right? And then this will just matches with our original equation, which is, okay, so these two are matching with each other, right? Because remember, we've just said this is the kinetic energy and this is the total energy. Through our way of working this solution out, we've successfully come to this step, which tells us that kinetic energy times psi equals to total energy times psi, which is the same with our assumption up here. Okay, so we have just went through some of the basics of quantum mechanics. We have talked about wave-particle duality. We've talked about the wave function psi, and we've also talked about three representation of Schrodinger's equation. The complete picture of quantum mechanics is very complicated, and it's beyond my knowledge of understanding for now. And in fact, in Schrodinger's equation, the partial derivative is actually a part of the multivariable calculus course, which is beyond my knowledge for now. So in order to understand what multivariable calculus is, I had to went on to Khan Academy and learn some of the basic concepts of multivariable calculus, partial derivative, del, some of things like that. Yeah, so this is everything we're gonna talk about today, and I hope you join us in our next video.